In this video, we're going to look at another application of derivatives. So we can use derivatives to approximate the change in a y value given a known change in the x value. So the methods that use this, there's two different ways to look at it. Okay, so one way is where we look at differentials. The other way, that's actually the same method, just different notation, is called linear approximation. Okay, so they're the same method, just different ways to approach. So we're going to talk about each of these here. So just to remind you, the slope of a straight line, remember we know is m, which is rise over run, which you can also write as delta y over delta x, where we think of delta y as the change in y and delta x as the change in x. So you've probably seen and heard this before. So in this section, we're going to be using this notation. Okay, so delta y is the change in y, and delta x is the change in x. Now this is the actual change. Okay, so it's the actual change because we're also going to be talking about the approximate change as well. So we know what delta y and delta x look like. So if I have x values, x1 and x2, then delta x is the difference between the two. So we could write that as x2 minus x1. Or if you want, you could solve for x2 and say that x2 is x1 plus the change in x. So plus delta x. Okay, so then delta y is going to be the change in the y values. So it's going to be f of x2 minus f of x1. And then if we use this other way to write x2, you see that this is actually f of x1 plus delta x minus f of x1. And this looks maybe sort of familiar. It looks like the top of our sort of limits that we were talking about earlier. So let's also recall when we used the limit definition for the derivative, f prime of x, which we also write dy dx, is the limit. So we used h for us, but this is the limit as delta x goes to 0 of f of x1 plus delta x minus f of x1 all over delta x. Okay, so if I did this with h instead of delta x, you might recognize it. So f of x1 plus h minus f of x1 all over h. Just the limit definition for the derivative. So when the derivative exists, what happens is we're sending that bottom, the h or the delta x, to be almost 0. Okay, so that we want the change in x to be very small. When that happens, we get dy dx, the derivative, is approximately equal to delta y over delta x. Okay, so remember that the limit is approaching that value. Okay, so when we're close to the sort of limit value, we should be close to our number. So maybe I'll just write that. Dy dx is what the limit approaches. So when we're close to the limiting point, our sort of y value should be close to what it's going to equal. Now, I'm going to say something here that maybe you won't like, but I've been kind of lying to you. So far in this course, we've been thinking about dy dx as a single thing, okay, representing the derivative, and something that we cannot break apart. Okay, but now we're actually going to start thinking about dy and dx individually. Okay, so because you can think of dy dx as approximately delta y over delta x, we can think of dy as the approximate change. Oops, I spelled that wrong. The approximate change in y. Okay, and dx, which is actually, because we know the change in x, it's actually delta x, but it's so approximate or not approximate, but it's the change in x. Okay, so y is the one that we don't know generally. So dy is the approximate change. So thinking about this as a picture, So let's say that I have, let's do my graph. I kind of want it to go, well, whatever. Let's say I have a graph like this. Okay, so here's y equals f of x. And then I have some point, let's call it here, okay, point P. So here's x1. This is going to be f of x1. And we talk about, so we want some change in x. And actually, let's just call it x instead of x1, so I don't have to write those. So let's say it's over here. So this is going to be x plus some change, plus some delta x. Okay, and then the y value is going to be f of that. So what's going on here? So maybe actually let's just do a different color. So this distance, this part is delta x, right? That's the known change in x. So this is also dx. Okay, now the distance, maybe I should, this is another point, say q. The distance, in the difference in height, this is our actual change in y. Okay, that's delta y. Actually, maybe I should have put it on the other side so that it's out of the way here. So the change in the height here, this is delta y. Okay, so this we already know. So what we're going to do is try to approximate delta y. And the way we're going to do that is to think about the tangent line. Okay, so if I draw the tangent line at point P, it's going to look something like this. Okay, so this is the line, tangent to f of x at point P. So what we're going to do is approximate the dy using the y value on the tangent line. Okay, so this change in height, this is what I'm going to call dy. And this is much easier to find because it's the change on a linear function as opposed to a curved, more complicated function. Okay, so I prefer to think of the differentials using the linear. So this is sort of the idea behind the linear approximation. So we're using the tangent line at a, so we think of P as a nice point. Okay, so something that we know. Okay, and maybe Q is a not nice point. So maybe I want to know the y value at Q, but it's hard to compute. What I can do is take my tangent line at the nice point and try to find the y value at my x, the x value I'm interested in on that. Because the shorter the distance, so the smaller dx is, the closer dy is going to be to delta y. Okay, so remember, the smaller the interval, the closer the tangent line represents the function. Okay, so this is the idea. So we can think of dy and dx as approximate change for y and x. So how do we compute dy? Okay, so that's sort of what I was trying to talk about there. So dy, if we look at it, think about this tangent line. If I was to go between this point and this point, what I've done is I've gone up dy amount and over dx amount, or delta x. So dy is actually the rise of the tangent line, the slope of the tangent line, I should say. And dx, or delta x, is the run. So dy is actually the rise of the slope of the tangent line. Okay, so what that means is if I compute f prime at x, okay, this is the specific x, the specific x value, okay, at the nice point, so at point P, this is going to be equal to the rise over the run, right? It's equal to the slope. So that means that f prime of x is actually dy over dx, so that's nice. Our notation still makes sense. Okay, whereas this is the rise and this is the run. And then we can rearrange to get that dy is actually f prime of x times dx. Okay, this is how we can compute dy, so our approximation for the change in y. This is the idea behind the differentials. So, for a function, y equals f of x, okay, whose derivatives exist, the differential, so that's what we call dx, is the differential of x. Oh, I already wrote that, sorry. Written dx is an arbitrary real number, so something that we get to pick. The differential of y, though, is written dy, and the way that we compute it is f prime of x times dx. Okay, so that's how we compute this differential in y. So, the reason this is useful is because for delta x small, so when we're close to 0, okay, dy by dx is approximately delta y over delta x. So if I solve for delta y, it's going to be approximately dy over dx times delta x. Okay, but delta x is actually equal to dx, so these things cancel, which means that delta y is approximately dy. So this is sort of convincing us that our approximate change of y, the change in y, dy, is a good representative for delta y. So let's just do an example using this technique. Okay, so suppose we want to compute dy for the function f of x is 5x squared when x equals 3, and our delta y is 0.1. Okay, so here we could just find the y value, but what we're going to, so we should be able to actually determine delta y because this function isn't so complicated, but we're going to use the differentials method. Okay, so the first thing I'm going to do is take the derivative. Okay, so f prime of x is 10x. Okay, so that means that dy, so maybe I should just make a note. So this x equals 3, this is our nice x value. Okay, so this is the x value we want to plug in. Okay, so it's f prime at my nice value, which is 3, times delta x, or dx. I guess I should use dx because that's what's in the formula. Okay, so f prime of 3 is 10 times 3, and dx, they told me, is 0.1. Okay, so this is actually 30 times 0.1, so we get 3. Okay, so my change in y, I would approximate to be 3. Let's compare. Because for this one, we can actually compute delta y. Okay, so the points, I'm going from 3, f of 3, to 3.1 and f of 3.1, right? That's x plus delta x. Okay, so f of 3, we just said, oh, no, we didn't. We said f prime of 3. So f of 3 is 5 times 3 squared, so it's 45. Okay, f of 3.1 is 5 times 3.1 squared, which if you compute that is 48.5. Okay, so delta y is f of 3.1 minus f of 3. So that's going to be 48.5 minus 45, which is 3.5. Okay, so you can see our approximation of 3 is fairly close. So it's pretty good. because we can actually compute this, we actually know delta y here, but that's not always the case. So we can also use this method to approximate, so we can use this method to approximate the change in y, but then we can therefore approximate the actual y value. Okay, so we know that delta y is f of x plus delta x minus f of x. Okay, so those are the change in the y values. Okay, and since dy is approximately delta y, then I know that dy is approximately equal to this. So if f of x plus delta x minus f of x is delta y, then it should be approximately equal to dy. Okay, now this f of x plus delta x, this is the y value we wish to approximate. So if we solve for this value, we're going to get that, so I need to add the f of x over. We're going to get that it's a f of x plus dy approximately. Okay, now, so the idea is that this is hard to compute. Okay, but these are easier, since we use nice point P. Okay, this is sort of the idea behind the linear approximation. I mean, they're the same, but it's just a different way to write it. So if y is f of x, so it's a function whose derivative exists, and for a small non-zero delta x, so dy is approximately delta y. Okay, so we had that already. And then if we want to compute the y value, f of x plus delta x, it should be approximately f of x plus dy, which we know how to compute dy. So this is f of x plus f prime of x times dx. Okay, so that's what we're going to use to compute this. Now I want to mention, so you don't need to memorize this, really. I mean, you can. But this is just a tangent line. Okay, so I'm going to draw you a picture here. I left the space. So it's going to be basically the same picture as before. Okay, so here's my function, whatever it is. And then I have my point P, so my nice point, and some point Q that I'm trying to approximate. So we make our tangent line, okay, at P, and so here is my x, I'm going to call it x1. Okay, here's my x1 plus delta x, so some amount over. Okay, and we're going to use this y value, okay, instead of the y value at point Q. Okay, so that's going to be how we approximate. Now, how would we find this y value? So for the point on the tangent line, so the tangent line has a slope f prime of x1. Okay, so that's our m. And it goes through the point x1, f of x1. Okay, so that's the point. So we can make the equation. So the equation is, so y minus f of x1 equals the slope f prime of x1 times x minus x1. Okay, that's the equation. So if I rearrange and solve for y, I get f prime of x1 times x minus x1 plus f of x1. Now, if I plug in, let's do this in red. Okay, so we plug in my point, so my x value that I want is x1 plus delta x. Okay, if I plug that in to get my y value, that's going to be the y value at that x value. So my y value should be f prime of x1. So everywhere I see this is my new x value. So I'm just going to put it right there, actually. That's the only, x1 is already known, right? So my only x value is that one. So this is going to be x1 plus delta x minus x1 plus f of x1. And I see that these cancel out. Okay, so I end up getting my y value is f prime of x1 times delta x, or dx, plus f of x1. So this is the exact same as above. So what that means is, instead, if you don't want to use the formula, find the equation of the tangent line at your nice point and plug in the x value of your not nice point. Okay, this is going to approximate your y value. So let's just do an example. Okay, so we're going to approximate the cube root of 26. Okay, this is not a nice number. Obviously, your calculator could compute it. Okay, and I'm going to do it both ways so you can see sort of the difference. So the differentials method is basically just use the formulas. Okay, which maybe because we're online, that might be the method you go to. I always prefer the linear approximation because I never remember what the formula is. So let's do the differentials first. Okay, like I said though, these two methods are doing the exact same thing. So, and in fact, before I start that, we want this to be a y value. So what I'm going to do is I'm going to let f of x be the cube root of x. Okay, so then what I actually want to approximate is f of 26. Okay, so now I'm thinking this is a y value. Okay, when x is 26. So for both methods, what I want is a nice point that's near the x value that I want to approximate. Okay, so what would my nice point be? So it's an x value where I know how to compute the cube root of it. Okay, so something that's close to 26 that is a perfect cube is 27. Okay, so 27 is equal to 3 cubed. So that means that f of 27 is going to be the cube root of 27 is 3. So my nice point is going to be 27 and 3. Okay, so that's my nice point. So using that nice point, my delta x, or my dx, is actually minus 1. Okay, so because I'm going from my nice point to my bad point, nice to bad, okay, this is 27 to 26. So that means that I need to subtract 1. Okay, so that's why it's negative. So that's my dx. So now I want to compute dy. So dy is f prime of my nice point, so 27, times my dx. So I want to compute the derivative. Okay, so f prime of x, we know this is x to the 1/3. So it's going to be 1/3 x to the negative 2/3, or 1 over 3 cube root of x squared. Okay, so I can compute that when I plug in 27. Okay, so dy is 1 over 3 cube root of 27 squared times dx, which is minus 1. Okay, so in fact, this is negative 1 over 27. So the cube root of 27 is 3, and I square that, I get 9, times by 3, I get 27. And then a negative 1 makes a negative 1. So that's dy. Okay, so f of x plus delta x, so my y value. So here this is f of 27 plus negative 1, okay, which is actually f of 26. That's the thing I wanted. Okay, using the formula, this is approximately f of x, oops, that's my nice point. So f of 27 plus dy. Okay, so that's going to be f of 27 I know is 3, plus my dy is negative 1 over 27. So I end up getting 2 plus 26 over 27. Okay, so I would say that the cube root of 26 is approximately 2 plus 26 over 27. Or you could make that an improper fraction. Okay, now let's try the linear approximation. We will have done the work already for some parts. Okay, so my nice point is the same. Okay, so what I want is the equation for the tangent line. So at the nice point. So the slope of the tangent line is f prime of 27, okay, which we already computed to be 1 over 27. Okay, and we know that the point, our nice point, is 27 and 3. So that means that the equation of the tangent line is y minus 3 equals 1 over 27 times x minus 27. So if I solve for y, this is 1 over 27 times x. So this is going to be minus 1 plus 3, so plus 2. Okay, so that means that f of 26 is approximately this when x is 26. Okay, so this is going to be 1 over 27 times 26 plus 2, which is 2 plus 26 over 27. So notice that this is the same as what we got above. Okay, now just to compare, I'm going to actually put the decimal here. So if you used a calculator and computed this, you get 2.962963 approximately. And where did I have the actual value? Nowhere. And if we actually compute the cube root of 26, let's just do that. It is 2.962496 approximately. So see, we were right up to 3 decimal places. Okay, so our approximation is correct to 3 decimal places. Okay, now this doesn't always work. I mean, our delta x is 1 is actually quite large. Normally we want things that are closer together. But for this function, it turns out there's not that much difference. It's because the function actually looks like. So the cube root function looks like this. So when you're, say out here at 26 or 27, the curve is pretty flat. Okay, so the tangent line is going to be very similar to the curve.